Thank you. So I actually had some queries. This is in fact the presentation which is called on your guide, The Guts of Unicode in Python. I took out the intestines in the name of good taste. So we're in Great America, which as far as I can tell is the gloomiest presentation room in the Santa Clara Convention Center. Very soporific. I hope you can find some sort of entertainment in my talk that you'll be able to stay awake. So I want to talk about Unicode in Python. Unicode in Python has a long history. So I'll start with this quote from GVR, which you can find on the unicode.org consortium webpage. I can't actually find when this quote was said. 2000. Okay, so this is much older than I thought. So modern programs must handle Unicode. Modern in 2000. Python has excellent support for Unicode and will keep getting better. And I would like to talk about the keep getting better part specifically. So I'll tell you about how Unicode was originally brought into Python, and then I'll explain some of the implementation challenges and how we've adapted to them over the years. So starting with the history. Python and Unicode 2, now that we're several years into the Python 3 epoch, it seems like a much naiver time. So Unicode in Python was introduced with PEP 100. This is the document, which is PEP 100, was actually circulated for several years before Python, the PEP process was introduced. So it got the first official PEP number. The two-digit PEPs are meta PEPs, essentially. And PEP 100 set out the most important details of Unicode in Python 2 that we know and love today, specifically the Unicode type, the codex module and encodings, and the infamous strier to Unicode coercion model. And also, as we're going to see, this is a relatively simple implementation. Unicode object.c was only about 5K lines. It's going to get much bigger soon. And another critical decision which was made early at this stage was that Unicode code points would be stored in an array of unsigned shorts. So this means that the encoding was essentially UTF-16. So if you had a character which is outside of the basic multilingual plane, then it would be encoded as two surrogates. And this would be visible to the Python level. Another interesting facet of this is that Unicode could be disabled with a configure option. Maybe you didn't want to distribute the large Unicode character database with your Python application. And so this configure switch still exists in Python 2.7. It doesn't work per se, but I have managed to hack a build in order that you can start the interpreter without loading any site modules. And so you can see Unicode is not defined in this build. And if you use a uliteral, you get a strier back, which in some way anticipates the recent PEP, where in Python 3 you can use a uliteral and get a strier back. So Python 2.7 had it first. Okay, so in Python 2.2, I mentioned briefly that the Unicode was always being stored as UTF-16. But it turned out that some people wanted to be able to access the entire Unicode code point range without dealing with a surrogate encoding. So PEP 261 added the enable UCS2 or UCS4 configure option, which lets you use UTF-32 as the internal encoding, which means that the data size is essentially a long 4 bytes. Well, long on Windows and 64-bit, but anyway. And so you get this configure option. And so you could, if you wanted your application to be able to process every Unicode point without dealing with a surrogate encoding, then you could use this configure option. And if this seems like an inelegant solution, it is, and the PEP acknowledges this. It says, this PEP represents a least effort solution. So in a way, this is going to come back to haunt us. So several more things happen in the rest of the 2.x series, but we're going to get to the more salient part of this talk now as we talk about Unicode in Python 3. So Unicode in Python 3 made it the opposite of an optional feature, right? Unicode can not be separated from the Python 3 interpreter. So I'm sure you're all familiar with the kind of changes which are in regarding Unicode in Python 3, but I put them up briefly to summarize. So specifically, str is now the old Unicode type, and bytes and text are separated, and you cannot coerce between them implicitly. And identifiers are Unicode. So the fact that Unicode had become such an integral part of Python 3 meant that it put new stresses on the implementation. And I'd like to examine some of those in depth before I talk about how the implementation evolved to meet them. So one of these has to do with interacting with the operating system environment. Every platform, it seems, has a different idea of how you should represent a path name. For example, Unix just has byte strings with a / character. If you can have any other byte in there except null bytes, and it'll just eat it up as part of the path name. Windows, perhaps more sanely, uses UTF-16. OS X sort of uses UTF-16, but it's dependent on HFS+, which does a strange normalization to it, which is almost a specified Unicode normalization, but not quite. And Python wants to represent all of these things as a str. So this works pretty well in Python too, because you can take any of these things and stuff them into a str and go back and forth between Python and the operating system. But in Python 3, when str is actually supposed to be a valid Unicode string, not all of these things can be turned into a Unicode string. In particular, Unix causes problems, because if you have a byte string like this with some strange bytes in it here, and Unix is happy to let you write to it, but the file name cannot really be turned into Unicode in any rational way, like UTF-8 or UTF-16. Of course, you could decode it with Latin 1, but that's not really any more sensible than doing it with any of these other decodings, which fail. So to address this, in Python 3.1 saw the introduction of PEP 383, called non-decodable bytes and system character interfaces. And the way this works is that at the OS file system boundary, or it's not, Python operating system boundary, we take bytes which cannot be decoded into, which are not in ASCII range, and map them into private Unicode use points, which the Unicode Consortium has reserved for the use of applications. And so you're able to map the bytes into Unicode, and you get a nice Unicode string. And of course, it has these private use characters in them, so it doesn't really mean very much. But when you pass it back to another file system call, as you often do when you've gotten a file name, then it's able to encode it and map those private use characters into the actual bytes. And so here's an example of that working. You have a file name. Here's the same file name, and and you can see how this works through the os.fsdecode and fsencode functions. So fsdecode takes this byte string and produces a Unicode string with these strange private use characters here. So these are high characters in the BMP, and fsencode does the same thing backwards. Okay. The other major problem which became more and more present was UTF-16 versus UTF-32 representation. Okay. So one of the major problems with this is that it was a build time option, but it affected Python semantics on the Python level. Specifically, if you had a narrow build and you tried to use a character which is outside the basic multilingual plane, then it would be encoded as two UTF-16 surrogates, and that was visible to the application. So this thing is one Unicode code point, but it is represented as a string of length 2 in a Python narrow build, and that narrow means UTF-16. And it's been encoded as two surrogates as Unicode data. Whereas on a wide build, the same character is actually a character, one character, and Unicode data properly identifies it as a symbol. That's a snowman, in case you're curious. Okay, the other major problem is that, especially in Python 3, UTF-16 wastes a lot of memory for ASCII strings because we're using Unicode for every Python identifier, and when you have a large Python code base, every identifier and every doc string is being encoded as UTF-16, and it's probably almost all ASCII, and so you're wasting 1 byte for every other byte of actual ASCII data. Of course, it compresses pretty well, but you're loading this all into RAM. And so this is on a narrow build. On a wide build, you're wasting 3 bytes for every single character, and so this is starting to become a major problem. And so a lot of these things were wrapped up and dealt with in Python 3.3 by PEP 393, flexible string representation. And the idea of PEP 393 is that you use the smallest representation you can for a possible string. So the way that works in practice is that if you're given a sequence of Unicode code points, you find the maximum one, and then you pick the data size for the entire string based on that. So if you have a string which is with the maximum code point is 255, then you can use 1 byte because you can represent every code point as less than 255 as 1 byte. And so that covers most of the European languages. And then if you want to be in the BMP, then you can use, if you're using a character in the BMP, then you get a data size of 2, and if you want to use the full range of Unicode, then the string will have a data size of 4. It will essentially be UTF-32. And so this is based on it's different. It can be different from every string. There's 3 different snowmen in Unicode. Did you know that? And so you wouldn't necessarily have to use the smallest possible representation, right? Because you can encode an ASCII string in UTF-32, as we were doing in every wide build. But an invariant of our implementation is that you always use the smallest representation. And this lets you do a few optimizations. Because, say, if you're comparing 2 strings which you're using a different size, well, then you don't actually have to compare them. You can just reject them because they obviously can't be the same because one of them has a character which has a larger code point value than the others. So, for example, an ASCII string can always use 1 byte. So this has quite a few implications for Python. The most interesting one on the Python level is that everything is now a code point. We have a proper Unicode abstraction, essentially. So there's no such thing as a narrow build anymore. There's no such thing as a wide build. The length of a string is always a number of code points in it, and you will not get a surrogate indexing into it string, which is very nice semantic difference. Because a lot of the time on narrow builds, people would test their programs, and it worked for almost everything, UTF-16, but then once surrogates started coming in, their program was buggy. So it's nice not to have that distinction anymore. The performance characteristics of PEP 393 are much more complicated, and they make the performance much more complicated. In many ways, it's a lot faster on ASCII strings than normal Unicode, because we can identify when we have an ASCII string, and then we can just use the operations on those are usually the simplest. So we can just use optimized memcimp or and lowercasing or uppercasing an ASCII string is a very fast operation, which we can do right away. And even for applications which are highly internationalized, this works really well because, as I was saying, every string in the Python interpreter is pretty much an ASCII Unicode string as far as code goes, and so you're still able to save a lot of memory and gain some speed through this optimization. Other things are more complicated because, especially to maintain the invariant, that we always use the smallest representation for a string, it makes your Unicode algorithms a lot more complicated because, for example, if you're replacing the Unicode characters in some string, then you have to be able to tell what the maximum code point will be in the resulting string. And depending on what you're replacing and replacing with, it can be very hard to tell what you're doing. So sometimes you have to do a pass on the whole string before you can actually do the transformation to figure out what the maximum code point is. This also made our implementation quite a bit more complex. You see, we'd already gotten up to 15,000 lines in the core Unicode implementation from 5 in 3.2, but after PEP 393 was implemented, it got up to 20,000, so it's more than a 20% increase. We also got macro horrors like this. This is how you get the size of a Unicode string. So you can do a couple function calls, a couple conditionals. I always love it how I can put up a piece of ugly code and everyone will laugh. It's one of the great pleasures of speaking. And part of this is because the CCAPI in Python 3.2 and all previous versions of Python, you were given very direct access to the Unicode string. So this is an example using the old CCAPI of a contrived function which counts the number of ASCII characters in your Unicode string. So essentially, this macro here actually gives you contents to the raw Unicode data buffer. And so PyUnicode will be a typedef to either a 16-bit integer or a 32-bit integer, depending on whether you have a narrow or wide build. And so this is a compile time choice in narrow versus wide builds. But once you have flexible string representation, this no longer holds true. And so in the new CAPI, this is what this looks like. This code would have to look like. So the PyUnicode kind macro tells you how long, what the size of the character size is, 1, 2, or 4. And then this actually gives you access to the raw Unicode buffer, but you see it has to be a void because we don't actually know how long it is at compile time. And then we have to use a macro to actually access the characters, which takes the kind and the data as input and actually figures out what size of it needs to index into the void buffer. But this PEP was introduced in Python 3.3, and we don't break the CAPI in between 3.2 and 3.3. So we had to figure out a way to maintain compatibility. And the result is even more complexity. Legacy strings, which is basically a compact string, which is a string based on the flexible Unicode representation, can also have another representation, which is the legacy representation, which is the buffer which this string wants to use. So this macro still exists. Well, it's not a macro, it's a function now. This macro still exists, but it actually creates a legacy representation if it needs to, and then hands it back to the CAPI. So that brings us up to the current Python Unicode implementation. And of course, there's still a lot more work to do. Some of that is performance improvements. A lot of the Unicode implementations methods, when they were ported to Python 3.3 and PEP 393, used kind of the simplest possible path. And there's work to be done to improve them, that can be done to improve them. You can do all sorts of clever tricks. For example, our UTF-8 encoder has become blazingly fast recently because of the optimization work of one developer, where you can try to decode it as ASCII because that's really fast, and then only fall back on slower UTF-8, full UTF-8 coding when you see that there's actual non-ASCII character data. We should try to implement more Unicode spec algorithms like BD and collation. That's a very large project, but something we should take on. And along with that, some more work needs to be done on the regular expression module, integrating it and with the new Unicode representation. And also, it's been missing Unicode features like character classes for quite a long time. So what lessons can you take from the evolution of the Python Unicode implementation? One is that global configuration options are bad. You should not be able to change the semantics of the Python language by changing a configure option. It just creates incompatibilities. And people don't know whether their code is going to run on some Python implementation or some Python or not. For example, most Linux distributions compile with Python 2 with wide builds, but the Python 2 Windows installer is a narrow build. So if you only test on one platform, then you can run into unpleasant surprises as you port. Also, don't make a configure option to remove a built-in type. So the other thing is that even when Unicode was first implemented in Python in 2000, Unicode was quite complex, and it's only become more so. But we've been able to adapt through the years to the increasing complexity and internationalization of Python software. And don't expose internal details through your CAPI if you are writing a CAPI. Sorry if you have to write a CAPI, but it's much better to have an opaque interface than to hand people buffers whose format you might later want to change. And a lesson for optimization, which I'm sure we all know well, but optimize for the common case. Lots of things are ASCII. And that's my talk. Thank you.
Hi. One thing that concerns me a little bit after these changes is that it has become much harder to debug code in a debugger if it contains Unicode. Unicode was already hard in Python 3 when you have to look at a trace back or figure out what's going on in the program. You had to cast it to wcar. And now to figure out what's in a string, what is the name of this function that crashed, and so on. It's all but impossible to do, for example, using Visual Studio or something. Has this been a concern that has come up? Is it just me, and are there any plans to improve this possibly with a compiler option to always store an ASCII version along with your string, something like that?
Well, actually, in the Python source tree, there's GDB, Python GDB plugin, which is enabled when you're debugging Python, which knows how to print Unicode strings. So and other Python objects too, so you can see what's inside a list a Python list when you're in GDB. So that's certainly what I use to debug Python Unicode. Configure options are bad because they change the behavior of your program, right? Try using GDB. I mean, it works pretty well.
I'm aware of one other programming language, Go, which has chosen to use UTF-8 everywhere.
Yes, UTF-8.
If you're programming in Go, you use UTF-8, end of story. And I wonder if you guys made any, gave any thought to something like that. There shall be one true encoding.
Well, I mean, well, yeah, that's what I'm going to talk. I'm going to talk about that after I figure out something else to say. Okay. So, I mean, we're not really in a position to tell you what encoding to use, specifically because it's the goal of the Python Unicode type is to provide a Unicode code point abstraction. So we can't actually store the data as UTF-8 ourselves, because we need to provide the ability to index by code point into a Unicode string, and since UTF-8 is variable length, you can't do that efficiently. I mean, and since we basically have to leave it up to the application to choose UTF-8. Our UTF-8 encoder and decoder are very fast.
So that's actually a really good segue into my point, which is question. All of the talk about strings and how to encode them is just thinking in terms of arrays, right? And indexing into arrays, and you're either doing a sequential access through the array, or you're jumping straight because you know that there's like 256. You know it's 8 bits, you know it's 16 bits or 32 bits. Have you thought about using something like a rope or even a skip list, or maybe some marginally more advanced data structure that provides order of log n access to a UTF-8 string, for example?
I don't think it's come up. No, it has, but log n is probably not good enough. I mean, constants. Thank you, Thomas, for the validation. We want people to think of Python strings as basically an array with characters in it which you can index into and slice in. It's a sequence, basically. It's not like a stream. It's just a property of the Python Unicode type, or str type as it may be, that it has to be constant time indexing.
Okay.
Grill me afterwards.